Hello everyone and welcome back to another video. Today I will be implementing Dijkstra's algorithm in C. Now in my last video I went over the theory behind Dijkstra's algorithm. So if you haven't watched that video already, I would highly recommend that you watch it first because it will explain how the algorithm works. So to give an example of what we're going to be making today, I've got a demo right here of the program. So this program will generate a grid, and in the grid we'll have weights between each of the nodes, and we can specify a starting node and an ending node, and then the algorithm using Dijkstra's will find the shortest path between these two nodes, and as you can see the path is highlighted as green. So without further ado, we'll just get started with it. So the first thing I need is a way to represent the grid. Now before I get into that, I want to quickly highlight that I've imported some libraries here. So we have the standard libraries right here we're going to need, and I've also got the priorityqueue.h header file included. Now priorityqueue.h, if I just quickly find it, this is an implementation of a priority queue in C, and the way it works is we pass in vector 2's, which are positions of the nodes in the grid, and you pass in a cost. Now the way a priority queue works is out of the scope of this video, but you can think of it as a queue, but instead of dequeuing based upon which element was added what was added first, we dequeue based upon the lowest cost. So if I have, let's say, an element A which has a cost of 10, an element B which has a cost of 5, it doesn't matter what order I enqueue these elements into the queue, element A would always be removed first. So element B would move first because it has a lower cost. So a priority queue is going to be used as we explore different nodes, and we want to explore the nodes which have the lowest cost to us first. And I'll show you guys how that works when I start writing the code down. So the first thing we're going to do is create the grid. Now the way I set this up is the grid is made up of multiple grid nodes. Now a grid node, if you remember the theory video, a grid node can be thought of as an individual node on a graph. So the node on the graph is going to have a position, it's going to have a parent node, which we can get to it from if it's being fully visited. It's going to have a cost to be visited, and that's the weight on an edge of a graph if you think about it. It's going to have a total cost to visiting it, and we can use that total cost to calculate the shortest path. And then we also need a way to know if the node has been fully visited or not. So I'm going to create a struct here called grid node. And of course it's going to have a position, it's going to have a parent vector, it's going to have a cost, a total cost, and a boolean called visited. So vector 2, if you guys aren't familiar with it, if I go back to priorityqueue.h, a vector 2 is just a struct which has two integers, an x and a y, and these x and y's are just coordinates on the grid. I also have this a macro right here called invalidVec2, and this is just a vector with the values -1, -1 for x and y, and we use this if we try to retrieve invalid coordinates in the grid, but I'll show you guys that in a minute. So now that we have individual grid nodes created, how are we going to represent the grid itself? Right, so the grid itself will be a two-dimensional array of grid nodes. Now why is it two-dimensional instead of just having one big array? Well, when you have two-dimensional arrays, we have rows and we have columns we can index, so it's a lot easier to work with rather than having to do it manually. So let's say we have a 10 by 10 grid. Instead of having one array with 100 elements and then we have to kind of think about it logically by splitting up every 10 nodes, we can just have an array which holds 10 other arrays, and each of those arrays have those grid nodes, or 10 of those. So it's easier to work with. So the way we're going to do that is we're going to have a grid node, two-dimensional array. I'm going to call it data. Then we have a row count, which is the number of rows the grid's going to have. And we will also have a column count, which is the number of columns the grid is going to have. So to create the grid, I'm going to make a grid create function. So this grid create function is going to return a grid, and we can specify some of the properties of the grid here. So that's going to be the row count, the number of rows, and the column count, which is the number of columns. So I'll create a grid right here. I'll set row count equal to row count. Column count is going to be equal to column count. And finally, data will be an array of grid node pointers. So pointers times by row count. Now the reason this is a grid node pointer rather than just a grid node is because, remember, the rows are just arrays inside this multi-dimensional array. So remember, the rows will just be arrays, so we need a pointer to an array, and inside of those arrays will be the individual grid nodes. So you can think of this as allocating memory for each of the rows on the grid. And this should be there. And we also have to allocate memory for individual grid nodes, so each of the columns in the grid. The way we can do that is by iterating over all of the rows. So I'll say int y is equal to 0, int y is less than row count, that's increment y. Then this row here, I'm just going to allocate memory for all of the columns. So size of the grid node is times that by column count. And then I'll go through each of the individual columns in this row through the column count variable. I'll create a variable called x, and we just fill out their fields. So we have position. I'm just going to set this to be a two-dimensional vector, and we'll say it's x and y, so the current index we're at in this loop. The cost will be randomly generated. Now there's a few ways we can go around the cost issue. So if you remember back to my example here, these numbers which are in the middle, this is the cost to visit the node. Now I'm going to make the cost be at most 1 digit in size, so that means it can be between 1 and 9. The reason I don't do two-dimensional, or rather like 2 digits for the cost, is because it's harder to format into this grid shape that we have here. So in order to do that, what I'll just do is I'll use a rand function, which we get from time.h, I believe, and we will just use the modulus operator on it, and I'll put 9. So the way I've done the cost here is we have the rand function, and this can generate very large numbers or very small numbers, but when I apply the modulus operator to it, it brings it down to a range of 0 to 8. Now I don't want to have a value of 0 be a value to cost, because that means the two nodes are directly next to each other, there's no distance between them, which is invalid. So I want the range to be 1 to 9. How can I do that? Well, I can add 1. So the minimum range will now go from 0 to 1, and the maximum range will be 9 instead of 8. So this gives us a total range for the cost to be 1 to 9. Now the total cost is going to be set to infinity. However, we don't really have a way to represent infinity in programming, but we can just use int max. And int max is a macro for the maximum size of a 32-bit integer. And this just makes sure that we don't have any problems with comparing costs between nodes. So we also have the visited attribute. I'll set that to false by default because we haven't visited the node yet at the start. And the parent node will be set to invalid vec2 by default. And once it has been visited and we can find a parent, we just update the parent field. So once we've done all of this, we can just return the grid. And that should be it. This should be the code that we need to generate the grid. Actually, I forgot something quite important. So here we have to write srand time null. This just ensures that we get random numbers from rand, because by default we can have some duplicate numbers which we don't want. So we're also going to create the grid here and just test out the code. let's say grid is equal to grid create 2040. That means we're going to have 20 rows and 40 columns. Let's compile that, and we got an error. I think I typed it wrong. Okay, 38 visited. No, I typed it wrong up here. Okay, that compiles. Let's run it. No errors. That's good. Now the next thing we have to do is create a priority queue, and I'm going to call this priority queue frontier. So yeah, frontier. So I'm going to create priority queue right here, frontier, set equal to nothing for now. Let's initialize everything to 0. Priority queue initialize. This is a function inside of priority queue.h. So as you can see, this just allocates memory inside the actual structure to hold the data in the queue. So its size is just the maximum number of elements the priority queue can hold. So I would just set that to be, let's pass in the frontier first. I'll just say that's grid.row count times grid.column count. We probably will never store this many nodes, or rather this many vectors inside of the frontier at a given time. But just to be safe, this is the maximum theoretical size we could have in the frontier. So yeah, in the frontier. So now that we've created the priority queue, we can define some variables to be our start and end cells. So say start cell is equal to 0, 0, which is the top left of the queue. Sorry, the top left of the grid. And vector to say end cell is equal to grid.row column count minus 1 and grid.row count minus 1. This is going to be the bottom right of the queue. So start cell is top left and end cell is bottom right, as you can see right here. So now that we've defined these variables, I'm going to explain what the frontier actually is. If you remember back to my theory video, I told you guys the process with Dijkstra's is first, we visit the unvisited cell with the lowest total cost, and then we just explore its adjacent cells. And we just repeat that process until we visited all of the cells inside of the graph. Well, how do we actually know what is the closest unvisited node with the lowest total cost? And to do that, we use the priority queue. So whenever we visit a node, if the adjacent nodes have not been visited fully, or rather they're visited, this parameter right here, this variable right here, visited, has not been set to true, we know that the node has not been fully visited, then we add it to the frontier, and we'll give it a cost, which is its total cost. And when we dequeue from the frontier to explore a new node, we can be sure that that's the closest node to our current node, because the priority queue always dequeues the element with the lowest total cost, right? So I'm going to first enqueue into the frontier the starting cell, and I give it a total cost of 0, because we're starting here, there is no cost to visit the cell. This is the start of the algorithm. And now we can start writing the actual code for the rest of Dijkstra's. So I'm going to run a while loop. Here we're going to continuously run this code until the frontier, as long as the frontiers are empty. So priority queue is empty is a function right here, as you can see. And if there's no elements inside of the queue, then this function returns true. So as long as there are elements in the queue, we want to run Dijkstra's. So the code inside of this loop. Right, that's the logic there. So the first thing we want to do is get the current node or the closest node in the frontier. The way we do that is by running the dequeue operation. Now the dequeue operation returns this struct right here, vec2 and cost. And this might be a bit confusing. Why is it just a vector? Because we passed in a vector, right? We enqueued a vector and a cost. So the way the priority queue works internally is it combines element and cost and stores it in a struct called vector and cost right here. So just that holds the vector and the cost. And whenever we return a value or we dequeue from the priority queue, this returns the vector and the cost together. Because oftentimes whenever we're dequeuing, you want to know the value and the cost that it had initially, because it's quite useful data. So instead of having to do some function to retrieve the cost before dequeuing, we can just get both of those pieces of information at the same time, which is quite useful. So we can say vec2 and cost. I'll call this current node because this is the current node we were exploring. So we'll dequeue from the frontier, right? And I'll create a variable here called current pos, and this is just the vector of the current node we're exploring. Although I can just, whenever I need to reference the position of the node, I can just do current node.vec2. I'm going to be using this specific attribute a lot, so I just create a separate variable to store it in to just save some time typing. Now at this point, we can mark this specific node as fully explored, right? Because the operations we're doing from now on is just exploring its adjacent nodes. So instead of just marking as visited at the end, we can just do it at the start. It's a bit clearer, usually, at least in my opinion. So now that we marked the node as fully visited, we have to explore all of its adjacent cells, right? Now how are we going to do that? Well, we need two things to explore adjacent nodes. We need a way to specify the direction of where you expect to find where you want to get the node from. So we have north, east, south, and west. And we also need some sort of function where we can just pass in this current node and pass in the direction of the node you want and see if there is a node there. And if there's a node there, we just pass back that node. So the first part of the puzzle is having a way to know which direction we want to get the data from or the node from. And to do that, I'll create enum to hold different directions. So we have grid direction, I'll call this enum. And this will hold different directions. So I have north, east, south, and we also have west. I'll also create a final value here called iteration end, and you'll see why I have that in just a moment. So I'm going to write a for loop down here to iterate over all the different directions we have. So I'll say for enum grid direction is equal to north, while direction is less than iteration end, I'm going to increment direction. Now, if you are new to C, you might be seeing this code and getting a bit confused. Like, wait, what? How can you increment an enum? Is there some weird structure internally? Well, an enum is really just an integer. So, if you guys aren't familiar with this, whenever I specify grid direction enum, I'm just giving these names right here. They're actually just integers underneath. That's how the compiler treats them. So, this will be set to 0 by default. This is 1, that's 2, 3, and 4. So enums are just named integers, and because of this property, we can iterate over them in the way that I did before. So right here, I set the first direction to be north, and then as long as the direction is less than iteration end, I increment direction. So what that means is, I start off at north, and then as the for loop goes, I increment from north to east, then to south, then to west, and then once we reach iteration end, which is the end of the for loop, we just exit the for loop. So that's the end. And this is why I added iteration end. It just allows us to loop through all the different directions. So this is quite useful. Now as we are iterating over the different directions, I'm going to need some sort of function. So let's go grid get direction or like grid get node at direction, right? Then we have to pass in the grid, and then we probably have to give it the current position and the direction we want. And what we expect this function to return is a grid node, a pointer to a grid node specifically, and I'll explain why. Let's call that node in direction. So we need some sort of function which takes in parameters like the grid, the position we currently have, and the direction of the node we want to get. And then we expect it to return a grid node from that, right? So how would this function look like? So I'm just gonna, I'll create it up here. So it's going to return a grid node, right? And then we will just pass in the grid. The current position is going to be a vector2, and then enum grid direction for direction. So, how's this going to work? Well, we have 4 possible directions we can encounter. We have north, south, east, and west. So, since this is an enum, we can just run a switch case statement on it, right? So, I'll first do that. We'll create a switch case statement. We have north, and we also have south, east, and west. Okay? So now what I want to do is check if a node exists at the direction the user specified from the current position. So what I mean by that is, let's say current position is 0, 0, the top left of the grid. So let's say right here, this is the top left of the grid. Now, if I try to get the node at north from this position, well, that's invalid because there is no node north from 0, 0. That's the start of the grid, right? And similarly, there is no node to the east. However, there is nodes from the west and the south. But if I take some other node, let's say this one in the middle, north, east, northwest, south, and east, they're all valid directions, right? They're all valid directions. There's nodes in each of the directions. So depending upon the position of the node, there may or may not be a node in the direction. And we need to take care of cases like that. So how are we going to do that? Well, I'll create an if statement specifically for north. Let's say if the current position of y minus 1, so that means whatever this position is, whatever the value of the node above it, we expect this index to be greater than -1. So that means it has to be greater than, the least value can be a 0 because 0 is the minimum value we can index, right? So if it matches this if statement, or if it fulfills this if statement, we'll just return the memory address of that grid node. So grid data at the current position dot y minus 1, and it's going to be the same one for x, right? Because we're not doing east or west. Now for south, we can copy and paste this code, but we'd have to change it a bit. So instead, when we're doing south, we have to increment y because remember at the top of the grid, the row has an index of 0, and at the bottom is going to be the maximum number of rows minus 1, right? Because we start counting from 0. So I want to check if current y plus 1 is less than grid.row count. What that means is I want the current position of y plus 1, so the row underneath, what has to have a maximum index of grid row count minus 1, because that's the highest value that we can index. That's the bottom of the grid, right? So remember, 0 is at the top of the grid right here. That's 0, and then this is grid.row count minus 1. That's the bottom. And similarly, this is 0 for the columns, and this right here at the end is grid.column count minus 1, because we start indexing from 0. So I'll just return this plus 1, and we can just modify this code for east and west. So x minus 1 is less than -1, and then just copy and paste this as well. Plus 1, so column count instead of row count, and this will be x. Right, this looks good to me. However, in the case that we can't find any node, so maybe we try to get a node in at north, and we couldn't find a valid node there because we couldn't fulfill this if statement. We just return null. right here. So now that we have the code to check if we get a node in a direction, we can start filling out the rest of the for loop. So to do that, I'll go back right here to the for loop, and what we need to do is first check if this direction has a node in it. So if node in direction is equal to no, right? Because if we don't have a valid node in the direction we specify, we just return no. So if it's equal to no, we just continue on to the next direction. If this is a valid node, then we can retrieve the position of this node. So vector in direction, I'll say, is node in direction at pos. Right? But what I'm going to do now is also create the total cost to move to this node. That's going to be total cost to move to node. Let's say, let's call it that. That's going to be the total cost of the current node we are at, plus the cost to move to this node, which is so node in direction. That's the cost to do that. So what I mean by that is we add on the cost to visit the node onto the existing total cost of the cell we're at. So the way I'm going to do that is grid.data at current position. So remember, this is the current node that we're visiting. Don't confuse it with the node in the node in the direction we're exploring. So current pos.x.total cost plus node in direction at cost, right? That's how we calculate the new total cost to move to this node. Now, instead of just assigning the total cost to be this value, you have to remember there are some certain edge cases we have to handle. Because sometimes, if a node, we might have visited a node before, and we give it a total cost, right? But let's say this total cost is less than that one. So let's say this total cost is greater than the original total cost. So if I did something like node in direction total cost is equal to total cost moved to node, what happens if the existing total cost of node is less than this new total cost? That would mean that we are providing invalid information to this node because there's a better path to get to this node already, so there's no point updating the value. However, if this value is less than the existing total cost, and remember that at the start each of the nodes have a total cost of int max, so if this is the first time we are visiting this node, this total cost to move to node will always be less than the maximum value of the integer, right? So that it handles the first case that we never visited the node. However, if you visited the node before and this is a new route to get to the node and this is a more efficient route, then we can also update it then. We can handle that case. So what I'll do is I'll say if total cost to move to node is less than node in direction at total cost, right? Then I'll update the information, the total cost. And also set the parent node of this node in the direction to be the current position. Sorry, the current current position. Because parent's a vector, right? Finally, if we have not already explored this, fully visited this node, then we'll enqueue it onto the frontier. Right? So that's the algorithm, pretty much. So let's just see if this actually works first off. I just want to check if it compiles. Okay, so grid get node in direction. This has to be a pointer, right? And I misspelled. I call it vector direction. It's vector direction, right? Priority queue. Is it init, right? I think it's. Oh, it's initialized. It's initialized. That's my fault. Okay, that runs. Okay, seems to be running fine. So now that we've explored all of the nodes in the priority queue, right? How do we generate the path? Now, if you remember back to the theory video I made before, the way we generated the path was through a process called backtracking. So when we fully explored the graph, we know that the end cell, this right here, the cell at this index, it has a parent node, and the end cell's parent node also has another parent node, and we can backtrack that all the way up to the node we started with, which is the start cell, the first node we enqueued onto the frontier. Now, what this means is the start cell's parent vector is invalid vec2 because we never update the parent node of the start cell. The reason why is because the start cell has a cost of 0, right, to visit it, and 0, no other node in the graph is going to have a cost of 0. So we can ensure that the start cell's parent node is an invalid vec2, which is -1, -1, right? So if you remember here, -1, -1, right here. So what we can do is just keep on backtracking, go through each of the parents, starting at the end cell, we just go through each of the parent nodes until we finally reach a parent node of -1, -1. And what we do is, in that process, we just add the coordinates of each of those nodes, starting from the end cell, to a array, and that will actually just give us a set of vectors, which are the positions of the path, right? The shortest path between the start cell and the end cell. So let's do that right here. So I'm going to create a vector2 array, I'll call it path, and I'm going to use calloc because this will initialize all of the data for us to 0 by default, which is useful. So the reason I'm using calloc is if I used malloc, let's say, so I did malloc, I would do this times by that. Then I have to do a memset right here, so that'll be memset path set 0 grid column count. So I have to do this. If I use calloc, it just does that all for me. So probably have to separate the size of each of the, so here in calloc, I have to separate, this is going to be the number of elements, and this is going to be the size of each of the elements, which is vector2, right? So we just save a little bit of space there, just a little bit less code. I also have a variable called path index, which is set to 0. This is just the coordinate of the current index of the path, right? So the current index we're appending from. So I'll create a for loop for this. In the for loop, we'll say for each grid node, right, I'll call it comment node, starting from the end cell, right? So get the node at end cell's coordinates. We will check if this node's parent node is not an invalid node. Or what we can actually do instead is just check if current node.position dot x, so y is equal to -1, and current node.position dot x is not equal to -1. So as long as it's not an invalid node, which means that we've reached this, which means that we've already reached the start node, I mean the start cell, we'll just increment path index, right? And in the for loop itself, inside of it, what we'll do is pass that path index. We'll just set that to be the current node's position, and then we will set current node to be the parent node. So we're just backtracking. Now, to test if this works, we'll just go over all of the different nodes. I'm just going to print out each of the coordinates in there. So say printf, let's say I, and then I'll say the position I, path at I dot x, path at I dot y. Does it compile? It compiled. And it did not work. Why did it not work? I think it might be crashing. So guys, we seem to have an issue before. It looks like I made a bit of a mistake assuming that the current position can be -1, or rather the current position is kind of an x or y value of -1, because the start cell has the position is going to be the index of the cell or the node in the grid, and no grid can have an index of -1 for either x or y. So the parent cell of the start cell is going to be the only cell in the whole grid which has a parent of -1, -1, the vector. So instead of checking what the position is of the current node, we'll check if the parent node, either the x or the y, is equal to -1. Now if I run the code now, it should compile, right? But the problem is we're missing the starter node because we get to 1, 0, but we don't have the starter node. So we have to manually add that in. Since this right here, we're stopping at the start node, so we never actually run the code here to add it into the path. So we have to do that manually. So we have to set path index to be start cell, right? And have to equal path index so we can print it out. Let's see. So I run that. Now we have all of the different coordinates in the path right here. So that's pretty nice. Now the last part of this is going to be printing out the actual grid, right? So how do we print out the grid? Well, the truth is it's quite complicated the way we do it. So it's going to take a long time if I try to manually explain it. So I'm going to do just copy and paste the code to print out the grid, and then I'll explain to you how it works generally. Because if I try to write it down manually it'll take quite a long time. So I'll just quickly copy and paste that. So the first part of it is this part. So let's see. We add, this is to print out the grid, and then also have to add in a function called vec2 in path. So that's going to be, let's see, go up and add this as well. So what's this doing, right? You may ask, what's it doing? Well, we're going over each of the rows inside of the grid. Then we go to each of the columns. What I'll do is I'll check if the cell that we're at currently, or the node, is in the path. And I do that through this function here, vec2 in path. Now vec2 in path, what it does is just goes through all of the different vectors in the path, and it checks if this element we provided exists in the path. If it does, it returns true. If it doesn't, it just returns false. So pretty simple. So if this cell is in the path, I use these special escape characters to print it out green, right? And I'll just print out the weight to get to there, rather the distance, right, to get to there, a green. If it's not in the path, I just print it out white, just like this. So in order to have the separators that we had between the nodes, right, in order to have those, I'll just check if we're not at the end of, we're not at grid.column count, so just checking as long as we're not at the end of the grid in terms of columns. We'll check if the vector's in the path. If it is in the path, we just print this out green. If it's not, we just print out white. So the reason it's if statements here is because I don't want to have these two dashes at the end of the grid, right, when printing out. I don't want to have dashes trailing off the end. So we just check if we are at the last element of the grid. If we are, if we're at the last node, I won't print out the dashes because we don't need them. Now, in order to have lines between each of the rows, I use this code right here. So of course we don't want to have rows. We don't want to have these pipes below the end of the grid. So we just check if it's less than row count. Y is less than row count minus 1. Then we just iterate over all of the columns. We check if the cell above the pipe and the cell below the pipe are both inside of the path. What that means is that the path is going up. So the path can either go north, it can go up, down, left, or right. So checking if the path is going up. If it is going up, we just paint the pipe to be green. If it's not going up, we just paint it to be we just make it white. Let me just print out new lines after that. So if I compile the code now and I run it, as you can see, we have the path being generated. And it might be kind of hard to see it this way, so I'll just quickly switch over to the terminal and I'll just print it out here. So let's say CLS and run. So we have the grid working with it. You can print out the grid. And we can also make this multiple different sizes. So let's say I want to make it a bit smaller, so 10 by 10. Run that, it works. I forgot to compile it. Let's do it again. It works. If we want to make it something massive like 50 by 50, actually let's do 50 by 80. Absolutely massive, right? This might take a little bit of time to get working, but yeah, it could not print it out properly because the word wrapping's there. That's a bit too big then. I'll just say 50 by 50. Let's try that. So the characters are wrapping around lines. So here, yeah, we can fit 50 by 50 on the screen, so it makes it. And you might notice that every time I run it, the path is different. That's because random numbers are random weights are being generated, so the path will be slightly different each time because there's a new optimum path. And you can also change this. Let's just set it back to 20 by 40. Let's say I want to, instead of doing the top left and the bottom right, I want to do the bottom left and the bottom right with the start and end nodes respectively. So what we can do is, let's say grid dot row count -1 here, and then grid dot column count -1. Then we just change this to be 0. So if I run this now, this will go from the bottom left to the top right. And I can also specify any node in between as long as it fits within the boundaries of row count or column count. So let's just say I want to do between 5, 2, and let's say 10, 19, or 18. Let's say 19. Let's try that. And there we go. That's the path between those 2 points. So yeah, that's the whole of the video. I'll put the source code for this entire tutorial in the description. And if you like this video, please like, share, and subscribe. I have a lot more videos like this coming up soon. And I made a video previously about variadic macros in C, and I think if you watched this far, you probably enjoyed that as well. So thank you for watching. I hope you enjoyed it, and I'll see you guys later. Bye.